All right. Thank you, everyone, for coming to this talk. My name is Sam Cassatt. I'm the founder of a company called Aligned. Aligned, does anyone know what that animation is on the right? This is Conway's Game of Life. Aligned is fundamentally about aligning the incentives of game theoretic systems, right? Because game theoretic systems allow all Web3 systems to exist. Conway's Game of Life is kind of an example of an epiphenomenal system, so it's sort of part of the theme of what I want to talk about today. The talk is called Hardware for the Next Generation of Web3, and the thesis that underlies this is we mostly think about algorithms, right? But I want to ask the question, pose the question to you, what would you design if you're a protocol designer, if you're an engineer in the space, what would you design if you weren't limited by hardware? If you're not thinking about how you are limited by hardware, I want to pose to you that you are, actually. Web3 is all about protocols, algorithms, data structures. This is what we mostly are talking about at this conference right now at SCC. So anyone remember eGold? So eGold was a platform that allowed you to basically do what Bitcoin does, but it was centralized. And it failed for obvious reasons because you can turn it off. Hashcash was another invention that was sort of shortly thereafter that. Does anyone know Hashcash, what it was originally for? For preventing email spam, but this basically invented proof of work, right? So you combine those things together, some Merkle trees, et cetera, you get Bitcoin. These are the things that have enabled the industry and let us sit in this room right now. Fast forward a little bit, Ethereum took that and extended that beyond just those data structures. And then finally, Zcash, right? So Zcash introduced this idea of zero knowledge proofs. Zero knowledge proofs are the first time that we have a different type of mathematics that's being used underneath this, right? But these protocols all need work, right? And when we say work, it's kind of a euphemism for actually you need a bunch of hardware doing a bunch of stuff underneath. This is not Satoshi, but I'll pretend that it is for a second. Does anyone remember who the second person to own a Bitcoin or mine Bitcoin was? There you go. So Hal Finney running Bitcoin. He was the second person to mine it, second person to have a Bitcoin, get sent a transaction. Back then, they were doing this on CPUs, right? That was fast enough. Hal Finney, this is probably a 2008 era CPU, so I tried to be historically accurate. Eventually, we moved this up. We started using GPUs because we can do it a lot faster for that same hashing function, just SHA-256 hashing. But that work, again, it's useless work, right? The only reason that we're doing that is just to slow down the mining issuance of Bitcoin. We're not doing it because it actually does something useful, right? FPGAs, this is actually a Butterfly Labs FPGA. If anyone ever tried to buy one of those? Yeah, they never really shipped them, but you could do it. They're a little faster. And then finally, obviously now we have these rooms full of giant ASIC machines doing this stuff. That was the progression of hardware, but it was useless work hardware, honestly. It really is just for doing that hashing algorithm. So I think there's some other examples of how hardware has defined what we do in a computing industry, right? So this is a normal looking stock photo of a data center. In normal data centers, we have servers in them. They run things like the early Facebook, the early AWS, et cetera. They have pretty standard architectures, just some computers networked together. But when Facebook started looking at how do we run multiple, like thousands of streams of video that all need to be transcoded into different regions and different formats and fit on 20 different kinds of phones, they came up with this thing called the F16 Data Center design. It's a completely different design. It has ASICs inside of it. That allow it to do switching. It has different control planes in the fabric. This totally changed data center design. This is actually an open source kind of thing. A lot of people worked on it. It totally changed the way that we think about how do you do video encode, transcode, stuff like that within data centers at large. And this now lets people, lets Facebook serve billions of simultaneous users. But you had to rethink the hardware in order to do that, right? Because they had a different kind of workload than you had before. So, what I want to talk about is proof of useful work. And what we're moving into, I think, is in the advent of a time in history, in the history of this industry, when we have computation, you can call it work, but you can call it just computation, that actually does something useful. It actually does something else. So Bitcoin just doing SHA-256 hashing. Ethereum, also doing hashing, CAC hashing, that's on a GPU or on an FPGA, most likely. In the early days, I don't know if anyone remembers this. This is like before it launched. People actually talked about maybe using like SETI at home or folding at home. So we can search for aliens, or we can do like drug research using using the Ethereum algorithm. That kind of went away. We just chose to do a normal hashing algorithm, but that would have been kind of proof of useful work. But then we have Zcash. Zcash uses Equihash, a bunch of useless Equihash kind of stuff, plus some ZKPs, which are useful. But then now we have this whole new generation of extremely computationally intense things to do for companies like Aztec, ZK Sync, Starkware, Aleo, Scroll, Ironfish as well. These are all companies that are doing something that requires something that looks like proof of work. It looks like heavy computation, but we don't really know what is this layer, right? What is the hardware that's going to run on, and how do we do that? How do we build that stuff? That is one of the things that Align is working on. I think there are two approaches that are happening right now. There's sort of a decentralization first kind of approach. Companies like Aleo, for instance, have built in to the way that they've launched their network a proof of useful work, right? The difficulty of the mining algorithm is a zero knowledge proof, right? So they just said, it's just like Bitcoin in terms of mining. You can see this is the mining reward, 100 Aleo per block. This is in a test net. But they just said, let's incentivize people to do a bunch of zero knowledge proofs, and let's have that be the mining algorithm. Scroll, this is a tweet from Scroll saying, in addition to the ZK EVM-based execution layer, we're building a robust outsourcing mechanism to enable a decentralized network of rollers to generate ZKPs. They're sort of thinking decentralized first. That hasn't really launched yet, but it's very, very close. That's like fundamental and core to the design. So I said, decentralization first in their design. That's one approach. I think it's a really good approach. And it's one of the things that we're thinking really deeply about. If you're thinking about the ZK EVM, for instance, Scroll is a ZK EVM. That's a lot of workloads, right? Because it's not just taking a tiny, tiny proof and trying to roll that through a GPU or something. It's actually a much larger piece of data, and we need to figure out how to do that. Then on the other end of the spectrum, you have, this is the roadmap of Starknet. At the bottom, you can see it says, coming soon for decentralized sequencers and provers, right? So they've taken let's get it to work first. Let's build Cairo. Let's have all this stuff. Obviously, they've been extremely successful. Maybe some people in this room know it very intimately, and they're right outside. But Aztec, ZK Sync, /Matter Labs, these companies have taken a similar approach. Let's build something that works, and let's figure out later, because we know it's centralized right now, we know that doesn't ultimately scale. It doesn't ultimately let us get that computation done in a scalable way, but we'll figure out later how to build a decentralized proving network. But the end result of this is the same thing that happened, the same evolution that happened in this hardware from like CPUs, GPUs, FPGAs, ASICs. My thesis, the thesis of Aligned, is that that's going to happen all over again within a different domain, namely in zero-knowledge proofs, and namely within other types of high-performance computing that are sort of hiding in the stack of web. So how do we actually accomplish this? A few things going on. So this is an example of a few things that are happening, right? So right now, there's something called the ZPRIZE. Have you guys heard of this? So the ZPRIZE is funded by Polygon, AMD, a few other parties. It's basically a competition. It's happening right now about how do we get this computation to be done in a reasonable, equitable, sort of efficient way that allows people to do it in a decentralized way, that allows people to build hardware. They're all aiming towards doing something open source, which I think is great. But if you look at some of the text from the description of the prize, they're talking about the FFT. FFT is a fast Fourier transform. It's a battle about space on the chip. Doing larger FFT on an FPGA, which is one of the things that we're using, starts to require special designs that are largely unexplored, except we're exploring them. When it comes to more than one card, you need to figure out how to coordinate them, right? So if you think about in this bottom right here, this is a sort of a diagram of the circuits of an NVIDIA A100 GPU. So the A100 is basically the flagship high-performance computing version of a GPU. It's much, much larger. If you can see on the side, on the very, very side, this is HBM, high bandwidth memory. So that's the same kind of memory that's in something like a graphics card. In the middle are the cores, these processing cores. The problem is, if you have something like, for instance, multi-scalar multiplications, fast Fourier transforms, et cetera, these things blow up to be much, much larger than might fit in a GPU. Actually, this one's probably big enough to fit a lot of computation in because this is the largest. Some of these come in like 40, 60 gigabyte sizes. But if you think about what's the average Ethereum miner using? What's the average person at home using? And even what's the average instance size of something that's in Amazon, for instance? You're talking about like 8, 12, 16 gigabytes. It's too small to fit something like this, a proof size of a large Stark, right? And so everyone's sort of asking this question, and I would contend that the reason why the people that are sort of going to figure it out later, like a a Matter Labs or a Starkware, et cetera, one of the reasons this hasn't been decentralized is because the problem hasn't quite been solved yet of how do you actually do this computation? How does it all fit in a way where we can do it at scale and we can do it in a decentralized way? These things, these A100 GPUs, they're very, very expensive. They really only exist in machine learning context. You can't, even if you wanted to rent a giant farm of them, an Ethereum mine size of them, you couldn't from Amazon or something like that. So it presents a huge set of problems that the industry needs to face right now. So this is sort of the point of my talk here, is that this is what we're aiming at solving. So one of the things you need to think about too is the general disjointness of the different types of proofs that are necessary in order to realize ZK rollups, in order to realize secure multi-party computation. These are all things that are, that are not yet explored, not yet understood. One of the things we're trying to do too is standardize this, right? Because if you look across domains, if you look across different types of computation that are available, then you end up with everyone doing something completely different, everyone having different proof sizes, everyone having different types of hardware that might be necessary for that. So when you think about this, and what our core competency is at Aligned is that we think deeply about how to stream information through chips. We think deeply about what does it mean to have memory clustered in different ways and different configurations. If you think about the most advanced teams that are making sort of GPU miner firmware that they ship out, maybe it gets you a little bit higher clock speed, maybe it gets you a little bit lower voltage or a little bit lower energy consumption. They're not thinking about this at scale. How do you take something that doesn't fit in there? How do you take 10 of them or 50 of them and hook them together? How do you make them then process an arbitrary amount of ZKPs that allow us to scale what we all know is the scaling solution of Ethereum, which is ZK rollups. And the industry isn't there yet. So we're trying to get there. I think we are, in many respects there. So one of the responses I usually get when we get our engineering team on the phone with another company that's designed something very intelligently about ZKPs is, someone told us you couldn't do that. This is a very simple and silly illustration of that thing not fitting in that thing. I'm sure that some of my engineers would find that silly, but that's the general idea: is that it doesn't fit. How do you get that through? We've come up with other ideas about how to do it, like for instance, recursive ZK proofs. That does scale a lot of things, but it also doesn't have the power of being able to compute the entire thing. So this is sort of our core competency. If you were to go to try to rent something from Amazon that not only had a very hefty kind of computational ability, but also the ability to access arbitrary memory, storage, throughput, supercomputer level interconnect. It just doesn't exist, and so that's what we're building. So what I want to contend also is this: this is one type of computation that we all know is really necessary, but there's sort of work, aka computation, that's just bleeding into the stack everywhere, right? So block proposer builder separation. This is pretty exciting. This is like enshrining flashbots, or enshrining not the word flashbots, into the next generation Ethereum roadmap, but we're calling it PBS. I think this will engender the creation of what some people are calling super builders, which is essentially validators that exist across different chains, are able to do things like compute commitments between chains and do atomic swaps between them. This is an emerging kind of field. This is a really cool paper by Flashbots. I don't think it's fully published yet, but this is about sort of cross-domain MEV and what it means to be a cross-domain validator, and either collusion or being the same validator across those different domains. To do that at scale, you need to be a block builder. And to be a block builder, what I would contend, and what I think a lot of people would contend, Vitalik also mentions this in his Endgame post. If you haven't read it, you should, about the coming sort of like centralization of block builders, which is okay. It's not necessarily a bad thing. basically being a block builder or being a super block builder is a supercomputing problem, right? How do you pack the most MEV into a particular block? How do you compute what MEV is going to look like 15 blocks from now? This is not something that you can run on a tiny server. This is something that is a whole new type of computation as well. Sort of, and beyond that, right? As this computation diffuses into the stack, we also have things like KZG commitments, which are part of dank sharding, which I love the name of. So it's dank, but it also was made by a guy named. Dank sharding has things that look like zero knowledge proofs in it. It's hiding everywhere. Computation is hiding everywhere, and we're not thinking about it as an industry in the way that we think, in the way that I think we should. So something from SPF the other day, he was like, 5 to 50,000 transactions per second is great. Solana also limited by hardware in many respects. Maybe they need a fee market too, but limited by hardware in many respects. But what does it actually take to get to 1 million transactions per second? You're not going to do that on a Dell server. So I would contend it involves hardware solutions, namely customized hardware solutions, in order to make that happen. So it's bleeding through the stack. It's sort of everywhere. And I want to return to this question: if you're a protocol designer, or you're thinking about your application on Ethereum or related chains or whatever, on ZK rollups, what would you do if you weren't limited by this stuff? Almost every ZKP team I talk to says, well, we tweaked the algorithm in this way so it would fit in a GPU, or it might in the future or something, right? What would you do if that weren't necessary? What would you do if thousands of transactions per second, hundreds of thousands of transactions per second weren't like that? So what Align wants to be, by the way, is an antithesis to the existing hardware companies in the space, which are mostly extractive. Nothing against Bitmain. Butterfly Labs in 2010, I think, said they were going to ship a bunch of stuff and never really did. Bitmain ships these things, they mine on them, and then eventually they sell them to the public once they're not mining on them anymore. We want to be a collaborative entity, right? If you're working on something that you think would benefit from different hardware, that you have a hardware problem that you haven't thought about how to solve, or you don't know how to solve, or someone told you couldn't solve, that's sort of our spot. Let's think about the stack in a bottom-up and a top-down way. I think everyone thinks sort of like, I have an application, and then I have another layer and another layer, and that's sort of, that software stack is really what most people think about. What we think about is actually that at the bottom of the stack, it turns into electrons and bits, and then it turns into designs, and those designs are our domain. By the way, we also are a full stack validator company. We do things up and down the stack, but one of our core competencies is to try to help this industry advance by advancing the science of not being limited by hardware. So, thank you very much.
Is there any questions? Question? 1 minute. 1 minute.
All right then.
Thank you. Just zero knowledge proof. Like how do you envision data centers validating zero knowledge proofs going forward?
So how do I envision validation of zero knowledge proofs going forward? I imagine a different data center architecture, right? So at Align, we're building a completely different architecture than you would normally think about. It looks a lot more like a supercomputer, highly interconnected, ability to share, workloads across different chips, ability to stream information through entirely custom designs. And so I think it looks a lot like that. It looks like a high-performance computing data center, and it looks like being able to serve arbitrary workloads in a way that's not currently done. You can't do it on AWS. You can't do it in a normal mining farm. It looks like a highly interconnected supercomputing fabric.
And when do we see that? Like timelines? When ZK snarks, we're starting to see this proliferate, but in that paradigm paper, they said this could be bigger than proof of work by orders of magnitude. Is that next year?
Yeah. So the question was, when are we seeing this? Paradigm says it could be bigger than proof of work. I think we're starting to see it right now. Most of these companies that I had in this sort of roadmap, this is the end of 2022, middle of 2023 as they decentralize these proving networks. And then it all depends on transactions per second and the adoption of that. I think most of us think that ZKPs and ZK rollups are going to get adopted pretty heavily over the next year or so. So it's going to scale with that. And then there's also a whole multi-party computation. So, the baseline protocol, Microsoft, SAP, the MPC Alliance, all these companies are working on how to use things like ZKPs for multi-party computation to replace basically, the Intel SGX chip. And so that's already real. We're already really doing this. It's only getting more exponential and bigger. So now-ish.
Yeah, thanks, Sam. So what do protocols answer when you ask them what would you do if you had unlimited space available for CKPs?
Yeah, they usually say, well, we would have designed the protocol a little bit differently, or we wouldn't have spent so much time on recursion, or we could add additional sort of like opcodes, or we could use larger sort of functions in what we're doing, and what we can do can go faster. Those are the domains that people usually think about. So sort of faster, bigger, less work for the developers, those kind of domains.
Yeah, so the architecture that you're proposing with the supercomputer stuff, it's inherently going to be centralized, right? And I guess the stock where people are talking about this, right now the block production or the prover production, the prover process is centralized, but at the later stage we'll decentralize it. What you're saying is counter to that, or the architecture that you're proposing.
Yeah. So if we assume that we are the only prover, then of course that's a centralized thing, right? I mean, there's a world in which maybe we become decentralized, or we somehow effectuate that. But the goal is, I think, of all these networks is to create an open marketplace for proofs, right? I hope that we're the biggest and monopolistic maybe, but as a business person should. But in general, there's no reason why this won't be an open market. We want to be one market participant doing this, and I think it will spur innovation in the entire industry, and people will compete on it, just as they did in other computational domains. But you're right. I mean, if we're the best, then we might win, and then we have to. Okay, sounds good. Thank you.